Hey everybody, welcome back. We are going to be talking now about how intermolecular forces affect chemical properties. And in the last slideshow, I kind of mentioned to you how they cause a bunch of different things. We talked about how intermolecular forces affect melting point and boiling point, how much energy it takes to melt or boil something, how much vapor can escape, the thickness, and the ability of something to dissolve in another substance, and we're getting into that now. So we're going to start talking about a few of these. The only one we aren't going to be talking about in this lesson is the ability to dissolve something in a specific substance, because that's honestly a whole nother ball of wax. So we are going to be getting into that a little bit later and get to that in a different lesson. But today we're going to talk about the rest of the properties, and hopefully we can help you kind of figure out how the intermolecular forces of a substance relate to a whole ton of different properties that we see for our elements. So the first thing that we're going to be talking about is a property called vapor pressure. So what vapor pressure is if I have a closed container of something, it is the measure of the pressure of the little gas particles that sit above a vapor, or I'm sorry, above a liquid. So I guess the best example of understanding that there is vapor above a liquid is if you've ever been driving past Lake Michigan on a really cold morning. In the middle of January, if you are driving past that, you may sometimes see the perfectly flat surface of Lake Michigan and then clouds coming off of the lake. Well, that is a situation where there is water vapor sitting above Lake Michigan, and when it gets cold enough outside, that water vapor actually condenses into these little kind of cloud-looking things. And so you're actually seeing the vapor from Lake Michigan sitting right above the surface. All liquids have a teeny tiny amount of vapor that sits above them. And what happens is, you can kind of see in this animation here, that what ends up going on is, if you think about it, all particles, unless we are at absolute zero, are moving a little bit. And as they move more and more, they have what's called kinetic energy. And what ends up happening is that sometimes some particles have a little bit more energy than the rest of the bunch do. And when that happens, those particles sometimes have enough energy to actually escape and turn from a liquid into a gas. So those few particles that have that extra little oomph of energy can turn into a vapor from the liquid phase. And what ends up happening is that they form that vapor above the liquid. And if I put that liquid in a sealed container, the vapor pressure measures how much essentially gas is above that surface. So what ends up happening is, like we talked about, the intermolecular forces are the glue that holds the molecules together with other molecules. And in the case of vapor pressure, what ends up happening is that the vapor pressure will increase because of two different things. One, it increases as the temperature of the liquid increases. So this is kind of a good little animation here. If you imagine the left is cold and the right is hot, particles that are colder move slower than particles that are hotter. And they do that because they have less kinetic energy. So what ends up happening is that if we think about these particles here on the left side, they are moving slower as a whole group. They don't have quite as much energy. And so because they don't have quite as much energy, not as many of those particles can escape. However, if I heat that vapor up, the average energy of all of the particles goes up because I'm adding energy to it by heating it. And when we do that, the number of particles that have that higher energy to escape gets higher. And you've seen this when you've been cooking like mac and cheese. As you cook mac and cheese, boil water, sometimes you'll see little wisps of vapor coming up. Those are molecules that have enough energy to leave and turn into the vapor phase or the gas phase without actually having to come to a full boil. So on average, there's always a few that can kind of escape. Okay, that's one way to increase your vapor pressure. The other way to increase vapor pressure is actually to have weaker intermolecular forces. So if you think about intermolecular forces as the glue that's holding something together, if the glue is not as strong, it is easier for that vapor to escape. So you can kind of think about these pictures also as two things that have different types of intermolecular forces. Intermolecular forces that are stronger are going to have stronger attractions between molecules. When that happens, it is harder for these vapor particles to escape and actually go from the liquid phase into the gas phase. If I have something that has weaker intermolecular forces or not as strong of glue, it is harder for my liquid to hold on to those molecules and they turn into a vapor really easily. So if you have ever walked into a dentist's office and it smells like rubbing alcohol, the reason why it smells like rubbing alcohol is because that rubbing alcohol has evaporated off and it's in the air and it has a very distinct smell. You get those kinds of behaviors from things that have very low intermolecular forces. If you have a liquid that evaporates really easily, we call it a volatile liquid because it transitions so easily from the liquid phase into the gas phase. So again, if your intermolecular forces are strong, not a lot of vapor can escape. If your intermolecular forces are weak, it does escape easily. The other thing that's affected by your intermolecular forces are your melting points and your boiling points. And when we talk about melting points and boiling points, it's really important for us to review the phase change diagram. So if you take a look at this chart here, and if you don't have this chart or unfamiliar with this chart, you are going to want to copy this down in your notebook. So take the video, pause it, get a copy down, and then we're going to kind of add some things to it. What this graph is showing us is the graph of if we are, let's say, heating up a sample of a solid, and let's talk about water because water is the easiest. Let's say we're heating up a sample of ice. What would happen is this graph represents on the x-axis how much energy I have added. So you can think about it as energy or you can think about it as time. So like how much time has elapsed as I've heated this thing up. And then on the y-axis, we have the temperature. So that's what's going on with the temperature. And when we think about a phase change diagram, we know that there are three phases of matter that we encounter: solid, liquid, and gas. And then if we go from a solid to a liquid, that's melting. If we go from a liquid to a gas, it's either boiling or what we call vaporization. It's condensation if we go from a gas down to a liquid, and it's freezing if we go from a liquid to a gas. So think about this chart here as kind of like a road that you follow. So if I'm taking ice and I'm melting it, I've got to go all the way here to this point until I freeze, or until I melt, I'm sorry. Then I go across this plateau till I get to a point where I've turned into a liquid. Then I go up again until I hit the vaporization point, and then I turn into a gas. So this is kind of like a diagram of all of the different phases and the energy that it takes, as well as the temperature change that happens. Now, a couple of points on your graph here. The melting point is the first plateau or the lowest plateau on your graph. And in the case of water, water's melting point is 0 degrees Celsius, which we know. The second plateau on our graph is the boiling point. And for water, under normal circumstances, the boiling point is 100 degrees Celsius. The chart that we see here is pretty much the same for any substance. The only thing that's different is the actual temperature for the melting point and the boiling point. But in general, the transitions that we see, whether this were a pure metal or something else like that, we generally see the same rough plateau action and the same rises as we do in water. Again, the only thing that's different in this case is the melting point and the boiling point. So there's a couple different things that go on in this graph that I want to talk about before we get going. At portions A, C, and E, oops, this is a mistake. It should be A, C, and E. What we end up happening is that we have the phase that that substance is existing in, and we are heating it up. So in A, we have the solid phase. In C, we have the liquid phase. And in E, we have the gas phase. And in any portion on this graph where you are seeing vertical changes in position, you have that substance in that particular phase, and all you're doing is you are heating it up. Okay, so if I'm in this A portion of the graph, I have solid ice, if I'm talking about water, and all I'm doing is heating up that ice until it hits that melting point. In the C portion of our graph, I have liquid water, and in the E portion of our graph, I have gaseous water. Okay, so what's going on in these parts of our graph is that we are increasing the temperature of our molecules. And the reason that the temperature is increasing, or kind of the two things that happen at the same time, is that as the temperature increases, the kinetic energy or the movement of the particles is increasing in those portions as well. So as I heat up my ice sample, what's going on is that the actual particles of water are moving faster and faster as I heat them up. The same thing happens in the liquid phase. If I go anywhere from the melting point up to the boiling point, as I heat it up, they move faster. As I cool it down, the particles move slower. And the same thing happens in the gas phase. So once I hit 100 and I'm in the gas phase, then I turn and my particles move faster. So anytime you heat something up, as long as it's changing temperature, your particles are moving faster, okay? Now, if you notice B and D this time, there are these weird flat parts, which we call plateaus in there. And this is actually kind of interesting. On the plateaus of our graph here, you end up in a situation where you have the actual phase change happening. And so as I transition from a solid ice to a liquid in water, once I hit the melting point, which normally again is 0 degrees Celsius, once I hit that melting point, the temperature change actually stops. So what'll happen is I'll heat up my ice, I'll heat it up, and then all of a sudden I'm gonna hit a temperature plateau. And what's gonna happen is the temperature will not change until every last little bit of water transitions from the solid phase to the liquid phase. And once that transition happens, then the whole sample starts to heat up again. And the same thing happens at my plateau for my boiling. So I end up hitting a plateau or a peak where my temperature stays at 100 degrees Celsius until that transition happens. And that is true for all substances at their melting point. And the reason for that is because at the melting point and the boiling point, you aren't having the particles move faster. They are actually overcoming their intermolecular forces at that point in time. Okay, so instead of having the particles move faster, what we are doing is causing a change in how the particles are attracted to each other because of that. And I'm going to show you that in just one second, but I want to give you a couple more terms. Okay, you're going to hear the term heat or enthalpy of fusion. What that is the energy that's required to make this transition happen. And in the future, we are going to be talking a lot about these calculations, but I just want to introduce the term here. The other thing is going to be heat of vaporization. So heat of fusion or enthalpy of fusion happens at this plateau, and it's how much energy it takes to make a mole of that stuff transition from one phase to the other. The heat of vaporization is the same idea, but it's happening at the boiling point instead of the freezing point. So for the heat of vaporization, it's how much energy it takes to boil a mole of that substance. Now, boiling is harder than melting, which we'll get into in a second. So you will always see heat of fusion is going to be less than heat of vaporization. But, and here's the part that we're going to get into with our intermolecular forces, the magnitude of our intermolecular forces will affect the temperature that something melts at, the temperature something boils at, and how much energy it takes to make that happen. Now, I want to show you a little demo with my molecules here of what happens in that phase change. So what I did here is I built you guys a model of ice. So this is a bunch of water molecules stuck together, and ice actually kind of forms this cool structure. It's got these little rings in there, and the waters are all linked together. All solids have this same structure. So if we are talking about any kind of solid, they form some sort of lattice. It's not an ionic lattice, but they form a rigid structure. So what happens is, as I have solid ice here, as I heat up my sample, my particles move faster and faster. And again, they are vibrating back and forth, okay? So I'm heating up, going faster, 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 faster. And at some point, I get to a situation where I have so much kinetic energy. Remember, each of these little magnetic attractions here, oops, I broke my thing. Good start here, guys. Each of these magnetic attractions is an intermolecular attraction or an intermolecular force that's happening, okay? So this is actually a hydrogen bond. So what will happen is as I approach my melting point, at some point, the kinetic energy that's happening in these molecules is going to be too much, and my very organized structure is going to fall apart. So when I hit that melting point, that big plateau, the big plateau is the releasing of that organized structure to the point where I get these kind of puddle, essentially, of molecules, okay? So the plateau is the transition from that very organized structure to this situation here. And then what's going to end up happening is as I go faster and faster and faster, my particles are going to be going faster and faster. And eventually, I'm going to get to a point where if I move these fast enough, you're going to see the particles kind of fall apart there. What will happen is when I hit the gas phase is when my liquid water, which is not very organized, has so much kinetic energy that I start to be able to have these intermolecular attractions fly apart. And so when we talk about gases, gases have basically little to no intermolecular attraction between anything because gases are very far apart and they kind of are moving really fast. And so when they hit each other, they usually don't stick together, okay? So when we talk about our graph, I'm going to go back here. When we talk about our graph, you can visualize this again. A is the very organized portion of our graph. Excuse me. B is where that very organized structure falls apart. And that transition that happens, the temperature stays the same as that organized structure falls apart. C, it's moving, it's that puddle that's vibrating faster and faster. Then we start to lose individual molecules, then they turn into the gas phase, okay? So how this ties back into our intermolecular forces is that if I have stronger intermolecular forces, they are going to have higher melting points and higher boiling points for those substances. If I have strong glue that's holding those molecules together, the intermolecular forces that form that very strong connected solid lattice are going to be harder to break apart than something that has weaker intermolecular forces. And as a consequence, I'm going to have to rock and roll those more at a higher temperature to make that happen. The same thing with the boiling point. If my stuff is stuck together stronger, I have to add more heat and get it to a higher temperature to get those gas particles able to leave the sample. If I have stronger intermolecular forces, they're also going to have higher heats of fusion and heats of vaporization. So that is, if I go backwards, the energy it's going to take to make that transition happen is also going to be higher. So it's going to happen at a higher temperature and it's going to take more energy to make that happen. Again, stronger glue means it's going to be harder to hold together. Okay? I'm sorry, stronger glue means it's going to be harder to pull it apart. All right, for intermolecular forces, substances that have stronger intermolecular forces are also going to have a thicker texture. So they're going to have, we call it a higher viscosity, which means it doesn't flow nicely. So something that's very sticky is going to have a strong intermolecular force. The other thing it's going to have is a higher surface tension. If you look over here at water, you've probably seen water bead up. Water beads up because it has a high surface tension. And a surface tension, what it is it's the ability for the molecules at the surface to hold on to each other and hold a shape. And this is what you see with like insects that can walk over water and things like that as well, okay? You will probably not be asked questions so much about texture and surface tension, excuse me, but you will see questions about these guys here for sure. Melting points, boiling points, heat of fusion, heat of vaporization, all that stuff. FRQs, they love to ask questions about that. Okay, so I'm going to, in the next little example video, walk through how to answer this question. The Lewis structures that we drew previously, we're going to keep rolling with those examples, have boiling points of the following. CH4 its boiling point is negative 161.5. CH2O, its boiling point is a negative 19, and CH3OH has a boiling point of 64.7. What I want you to do is I want you to tell me why compound number 3 has the highest boiling point compared to compounds 1 and 2. So take your time, try to answer that using intermolecular forces, and then in the next video, I will go through and explain that. All right, good luck.